Students, in first video we had seen about introduction to OR. Then later on we had seen 3 videos which are on formulation of an LPP. Also we had seen to find the solution to the LPP using graphical method. In all those videos, some of the words like feasible region, so optimal solution, solution, convex set, such words are came there, extreme points and so on. Now let we see the definitions of those things and also some more definitions which are required to our next videos. So let me take some definitions. Some definitions. So my first definition is of solution. Now you know the linear equation has a solution, means those values of variables which satisfy the constraints are the solution to that equation. Now here also the same thing, the values of decision variables, which or the values of decision variables. Now we had assumed the decision variables as xj. J, you know, we had taken in general form this j going from 1 to n. So xj, j from 1 to n, which satisfy the constraints only, are constraints only, is called solution to that LPP. Now similarly the next definition is of feasible solution. Now this feasible solution is one of the type of, it is also the solution, but it satisfies the non-negativity constraints also. So any solution, I must write, it is the solution but it satisfies the non-negativity constraints. So any solution that also satisfies the non-negative or the non-negativity constraints is called the feasible solution. To that LPP. That is, the values of xj that satisfy both constraints, that satisfy both type of constraints, means are given constraint as well as the non-negativity constraints also, both type of constraints simultaneously, is the feasible solution, is the feasible solution. When the constraints are not satisfied simultaneously, the LPP has no feasible solution, then it is called infeasible solution. So when the constraints are not satisfied simultaneously, means what? Some of the constraints are satisfied but some are not. So that is not the solution. Simultaneously, the LPP has no feasible solution. Then it is called as infeasible solution. Then it is called as infeasible solution. Now let me write down one note that if LPP has all constraints are of less equal type, then such a LPP has no infeasible solution. Such a LPP has no infeasible solution. They always have a feasible solution. If all constraints are of less equal type, they always have a solution, and that solution satisfies our both constraints. So that is feasible solution, means they don't have infeasible solution. Now the next definition is of convex set. In one of the problem of graphical method, I had already taught you about convex set. Now a set is said to be convex if for any 2 points in the set, the line segment joining these points, must lie in that set. Means what? Whatever the region given to us, in that one, if any 2 lines are, any 2 point we are taking, and we will join those by the line segment, then that line segment must lie in the same set, then such a set is known as convex set. So whenever we get a feasible region, that is always a convex set. But if the region is not feasible, then it is not a convex set. Now let me take some example. For example, the first one, suppose I will take a circle. Then let me take the second example as such. The third example will be, suppose fourth one, and one more let me take. Suppose this is our feasible region here. So now look at them. Now any 2 points we will take in this circle, and if I join them by line segment, then that line segment is completely lying in that circle. Whatever points we are taking here, any 2 points we are taking here, also the point on the boundary and the inside point, all those are what lying in same set. So this is what a convex set. Now here, if I take these points here, now this one also lying in a same set. But if I take a point here and here, and if I join them, now it will come outside. The whole line segment doesn't lie in a same set. So this is a convex set, but this is not a convex set. Now look at here. Now here I will take any two points. Then if I join them, then that also lying in a same set. This is also a convex set. What about this one? Now you can easily observe, if I take simply here also the point, that line segment will come outside. Here also if I take the points, then line segment will come outside. Means this is also not a convex set. What about this one here? This is our feasible region, suppose, or this is our set. This part is empty. So now here, if I take points here, then that line segment will lie in a set. But if I take point here, then that line segment will come outside. It is not in a same set. So this is also not a convex set. So here, what can I say? Here this 1 and 3 are convex sets, while second, 4 and 5 are not convex sets. Is it okay to you? Okay, let me go towards the next definition. So our next definition is of feasible solution through convex set. Feasible solution through convex set means what? Our feasible solution, if exists, then whatever region we are getting, you can observe in graphical method, every time that feasible solution space or the feasible region is a convex set. So here the feasible solution space, feasible solution space always constitutes a convex set. Now the next definition is optimal feasible solution. Optimal feasible solution. Now you know, optimal means either maximize or minimize. The solution or any feasible solution which optimize the objective function of LPP at the extreme point of feasible region. Already we had taken the examples on graphical method. In that one we are checking the values of our objective function at the extreme points of our feasible region. So if it gives us the maximum value if the problem is of maximization, and if it gives us the minimum value if the problem is of minimization, then that is our optimal value, and that such a solution is known as optimal feasible solution. So here let me write any feasible solution. It is a type of feasible solution, that is because it lying in a feasible region. A feasible solution which optimize means what? Either maximize or minimize. Maximize or minimize the objective function. The objective function of a LPP at the extreme points of feasible region is called optimal feasible solution to that LPP. This definition guarantees that the LPP has optimal solution if any always occurs at extreme point of our feasible region or a feasible space. So this implies, I can say this implies the LPP has optimal solution if any always occurs at extreme points of the feasible space Now let me take one more definition, that is of extreme points. What are extreme points? The corner points of feasible region are what? Extreme points. So the corner points of feasible region or a feasible space are called extreme points. Now let us go towards the next definition. Now the next definition is of basic solution. Basic solutions. Now here, as in general form we had considered, there are m linear equations in n unknowns such that n is greater than m. So here let me consider, as a general form, let us consider a system of m linear equations in n unknowns. Such that n greater than m. Now suppose n is greater than m. Then the solution can be obtained. By setting n minus m variables equal to 0 is called as the basic solution. To the given system. to the given system. For example, if n equal to number of variables, m equal to number of variables, that is same as number of unknowns. So m equal to number of linear equations. Number of linear equations. If we setting n minus m variables, if we setting n minus m variables equal to 0, then remaining variables equal to, what are the remaining variables? Remaining variables, total number of variables are n. So the remaining variables are n minus m. That is same as n minus n plus m. Means how many variables are left? M variables. And as these m variables are remain here, these m variables are known as basic variables that are not setting to 0, while those n minus m variables we are setting to 0, that are known as non-basic variables. So here the remaining variables remaining m variables are called basic variables. These are known as basic variables that are not setting to 0, and the n minus m variables setting to 0 are called non-basic variables. Non-basic variables. Is it clear to you? We are taking n variables and m equations, and we have to set n minus m variables equal to 0. Then the remaining variables are m, and those remaining m variables are known as basic variables, while n minus m variables are known as non-basic variables. Here we are taking n greater than m. So obviously n greater than m, then n minus m will be some positive value. Now further, if all variables are greater equal 0, then solution is called as the feasible solution. Means all basic as well as non-basic variables, all are greater equal 0, then that is what a feasible solution. If all basic variables means that are not setting to 0 are strictly positive or strictly greater than 0, then the solution is called as the non-degenerate solution, otherwise degenerate. Or if one or more basic variables are less equal 0, then the solution is called as the degenerate solution. If basic variables are positive, that is non-degenerate, otherwise degenerate. That is same as if basic variables are less equal 0, that solution is degenerate. If not, then it will also non-degenerate. Now, in next video, we will see some problems to find basic feasible solution from the given system with the help of this method, that number of variables, number of equations, then consider the setting n minus m variables to 0, and then find out the basic feasible solution if exists, and also we will check it is degenerate or non-degenerate. Thank you.